I'm Maurizio. I work in the compiler team in Oracle. You may have seen my name in the compiler dev mailing list. I've been working on a lot of support for language features such as lambda expression, type inference, local variable type inference recently. Today I'm not going to talk about any of that. So I'm going to talk to you about a project that I've been involved with for the last year or so, and I'm very excited about it. It's called Project Panama. And the goal of this project is essentially to bring closer Java with native code. Of course, Java has a tool for interoperating with native code. It's called JNI. We all know about that. Actually, quick show of hand. How many of you have ever used JNI in this room? OK, for a bit amount. OK, good. So I'm not going to talk about something completely unknown here. So Java native interface allows you to declare a native method. A native method is just a method without a body. So in certain ways, it's similar to an abstract method. But the difference here is that the implementation exists somewhere, just not in Java. So the VM must be able to find this implementation by looking up some symbol in some native libraries according to some name mangling coupling. And all this process is specified by the VM specification. And typically, developers use native methods in three cases. When they need to reach for interoperability with legacy code that is hard to rewrite, or when they want to access functionality that are not available in the JDK, although that's going to become rare. And third case is when they need to improve performance, or they feel they need to improve performance, because as we shall see, this is often a misguided attempt. So the relationship between Java and native methods, I would say, is at the very least ambiguous or ambivalent. So as you can see from this chapter in a very popular Java book called Effective Java, the second edition, Joshua is basically telling us, well, stay away from native methods. It's probably not something for you. A lot of functionalities are available in the JDK. You have just-in-time compilation. Why would you write a native methods? And that's kind of the scenario that we had around 2008. The JDK was getting bigger. For example, in JDK 7, we added NIO2 with file system watcher support, a lot of features that were previously only available at the native level. And the just-in-time compiler just kept getting better and better. So you can just run your application on a newer VM, and it just got faster without doing anything. So the result was that essentially using native method was a tool essentially for experts. Things like people like JDK developers or people that were maintaining very performance critical frameworks. Of course, this recently all started to change. As you may know, with the rise of machine learning, there's a lot of interest in trying to get things like numeric computation, linear algebra computation in the possible fastest way. And well, turns out this computation luckily are very parallelizable. In fact, they are called embarrassingly parallel, and they can take a lot of advantage by using a massively parallel architecture such as the one provided by modern GPUs. So you have like a device with 100 cores, you want to take advantage of them, so you can use GPU acceleration for doing a lot of this stuff. And it's no surprise that a lot of framework for doing deep learning jumped into the GPU train. The problem with this is that a lot of the libraries that provide acceleration to be able to offload the computation to the GPU, they are native libraries. So you can't access them directly in Python or Java or any other language. You have to reach out for the actual library that provide that support. And so if this were a movie, we could call it like a native method strikes back. And in fact, if you look at Effective Java 3rd edition, well, the number of the chapter has changed. Now it's not 54, 66. But the message here is that, well, if you are a performance-conscious developer, you may consider using native methods for things such as numeric computation and things like that. There are good libraries available out there, and you may just want to take advantage of them. So sometimes you just have to go native. Maybe you want to do off-CPU computation using CUDA, OpenCL. Maybe you want to do a little bit of deep learning, graphic processing. All the major graphic or rendering APIs are native libraries. Or maybe just using a popular library that is available there, like OpenSSL, SQLite, or V8 for JavaScript. And the best thing that a language or a platform can do at this point in time is actually to lower the activation energy that is required for a programmer to access to those libraries. So if it is very clunky, well, it turns out the programmers will never take advantage of those libraries. And the Java solution to all this is JNI, which is a very general framework, but it's also very hard to use and very error-prone when you just want to be able to access a native library. So this is a very simple example. I just want to call a getPid system call. I want to do that through JNI. And so I write my class, I put my native method called getPid, and then I have a client class that just create a new instance of this class and then call the getPid method. So it looks pretty simple, okay? You can see that system.library in there, so it's probably hinting at some more complexity. And the real workflow, if you are using JNI, is that you start from this getPid Java source file, you compile it with Javac, but giving it a special option called -h, which will also generate an header. So you get both a class file and an header file. And this header file will contain the entry point that the VM will look for whenever you call the native method. So now we have, of course, to implement the function. And we have to look for the header file that is containing the definition for the getPid system call. And then we have to compile everything with our platform compiler, be it GCC or Clang. And we get a shared library out of all this. And if we put the shared library in the right folder, we cross finger, we pray whatever God that we want, and luckily the VM will find it and we'll be able to resolve our getPid call. So that's all the process that you have to go through just for a single call. And in terms of code, this is kind of what's involved, right? There is a bit of Java code on the left that you have to write. There is a bit of C code and header file in the middle that is likely generated by Javac. And then there is the native code on the right that you have to write yourself. So there are a lot of things that can go wrong here because, for example, the library can be updated, and maybe its signature will change. And so you will have to update your C file. Maybe you will have to rerun Javac with the -h option to regenerate the header file. And of course, you can make a mistake in putting the library in the wrong place, and the VM will not be able to resolve the native method call. But there are also more subtle effects. So whenever we use JNI, whether we like it or not, we get an extra JNI env parameter, which is essentially like a pointer to the whole VM. You can use it to do Java method calls, field access, creating objects, and even throw exceptions. And this is important because the VM has to guard against this kind of stuff. It knows that whenever it calls to a JNI native method, well, there is Java stuff that can come out of it. So there is some special guard that the VM needs to put in place in order to be able to transition to the native code in the first place. The second problem is that, as we can see here, we are getting a receiver object, which is very cool because, well, we are getting something that we can put our hands on in the native code, this JObject parameter. But it actually indicates that there's a lot of complexity in the VM in order to actually make this object available to the native code. Because, you know, the garbage collector is moving objects around all the time. So it's not enough to just expose a pointer to the object. This pointer will keep moving. And so in order to expose a stable pointer to the native library, the VM has to do some work. It has to transform this Java object into stable pointers that are called JNI handles. And this is, of course, again, takes work. And if you look at our implementation here, we are just calling the getPid function. We are not using the JNI parameter or the receiver. So all this work is wasted. And if you are brave enough and you want to take a look at a great talk by Cliff Glick, there is a YouTube, it's available on YouTube, and it's called Why is JNI Slow? And it will show you all the assembly that hotspot VM has to generate in order to just be able to jump into that system call. So let's try to evaluate how JNI is doing in letting people access native libraries. Well, the good part is that the framework is very rich. It allows bidirectional interoperability, so not only we can call native libraries, but we can also go in the other direction. We can actually have the native code do some Java stuff, and that's cool. The bad part is that there's no support whatsoever for modeling data that is off the Java heap. And that's a problem because most of the developers then have to invent solutions, either using unsafe, which is, well, with modules is kind of harder to get your hands into, or using byte buffers. There's no direct support for kind of modeling a C struct in Java. And, well, to give you an historical, the first version of JNI actually represented objects as C structs. And that was great in terms of modeling of heap data, but it was also very unsafe because then you depended on the particular layout in which the VM decided to choose on that particular day. So JNI from version 1.1, it was updated not to rely on layouts generated by the VM anymore. So as we have seen, the just-in-time compiler cannot really do much for optimizing JNI code. It has to be prepared for the worst possible case, which is like this native code is going to, I don't know, allocate objects. So it has to set up the machinery so that the GC can actually look into the stack. And the ugly part is really that the workflow is convoluted. We are essentially asking Java developers to write native code and build native codes, figure out what is the magic incantation that they have to pass to GCC in order to produce a shared library and all of that. And as an Oracle employee, I'm also a little bit wary of the complexity that this is asking to the VM. Over time, we have been acquiring a lot of addition or extra features of JNI, for example, critical sections, to avoid some of the latency cost that is added by JNI. And this stuff keeps adding complexity over time. So we're kind of trying to reduce the complexity and come up with a little bit of a saner model to call into native code. So the vision of Panama is to allow Java developers to easily access native libraries, no matter which language are they implemented in. So C, C++, assembly, Fortran, you name it. And to do that, we don't want to use native methods. We want to use something else. So the idea of Panama is to use interfaces with annotations. So metadata, and this metadata will capture some of the information that was available in the native code, and it will be passed to a runtime component called the Panama binder that will be able to generate on the fly an implementation for these interfaces. And we'll see in a minute what that means. Since this implementation is generated on the fly, it can be trusted by the JDK, so the JDK can make sure that nothing bad is going to happen. And so we probably stand to reason to think that we can get rid of a lot of complexity that is associated with JNI calls. There is also a goal of Panama is to provide a rich API to access off-heap data, because we want to move a lot of the boilerplate that was that often surrounds JNI native code, and we want to express all the boilerplate in Java. And if we do that, if we are successful in doing that, then the just-in-time compiler can optimize it, so we can get better performances out of it. So the result is no more native methods. So this is what calling getPid in Panama would look like. As you can see, there is an interface here. It's annotated with a special annotation called native header. This native header annotation has to list all the symbols that we want to get access into. And as you can see, for each symbol, we have to provide this little DSL that describes what is the layout, the native layout for this function. So in this case, it says it takes no argument, it returns a 32-bit int. And I don't want to dive too much into the details of this DSL. It's not really the goal of this talk, but just that there is a way to express most of the stuff that is available in native code with this DSL, as we shall see later. So once we have set up this interface, we can just call the binder. So we say libraries.bind, We have to give a method handle lookup just for the context, and then we just pass the class literal of the interface. And this will generate an implementation on the fly that I can then use in order to call my getPid function. So there's no more native code involved here. The binder does all the heavy lifting of resolving the entry point of the function that I want to call and just go to it. So this was the Byzantine workflow of JNI, and with Panama we can reduce it down to this. So there's no more compiling with extra flags, there's no more writing native code or looking at header files. It's just straight Java code. As I said, there is also a rich API to model off-heap data. Of course, getPid is a very simple call, right? It doesn't take any arguments, it returns a primitive, but as you try to make a real-world library to work, you soon encounter stuff that takes a pointer to struct or pointer to a primitive. And so in Panama, there is this API point called pointer, which models a pointer to off-heap data. And it's really a triple of information. It has an address, it has a layout that describes basically what is the layout of the memory region that the pointer is pointing into. And it has a carrier type, a Java carrier type. The Java carrier type is used, for example, in the reference operation, when I want to extract data from the pointer or I want to put data into the pointer. So the X in the pointer X API point is going to define what is the Java type that I'm going to use with it. All the life cycle of pointers are managed by an abstraction called scope. You can think of it like ownership. So all pointers belong to a certain scope. If the scope is alive, you can dereference the pointer. If the scope has been closed or is no longer alive, then you get an exception when trying to operate on that pointer. And then there are, of course, arrays, which are essentially built on top of pointer. They are essentially a pointer to the base element of the array plus a length. This is an example of how you can get off-heap access working with Panama. Of course, we have to change our function. Now we are not calling getPid anymore. We are calling string length. And string length, if you look into it, it's accepting a pointer to a car, which in Java is modeled as a pointer to byte. So in order to be able to allocate an off-heap buffer like that, we first of all have to create a scope. And we do that in Panama, coupling it with try with resources. So scope is an auto-closable interface, so you can use it in a try with resources. And the block of the try with resources denotes the region of your code in which it's safe to operate with the pointers that are coming out of your scope. Once you have a scope, you can call one of the many allocation methods that are provided by scope. In this case, we just want to create a string, so we'll call the allocate C string that takes a Java string and returns a zero-terminated C string back, a pointer to it. And then we can just pass the pointer to the native function, and the binder will take care of extracting the address and passing it to the native function. So of course, as you move forward and try to support more use cases, there are lots of stuff that you need to support, such as structs, callbacks, and Panama as a story for all of this. I don't want to dive too much into details of this example, other than just to point out that it's possible, for example, to make structs working with Panama. Panama models structs using interfaces with annotation. So in this example, I'm using a function called clock getTime. This function takes a pointer to a struct called timeSpec. And I can model this struct in Panama using an interface and putting an annotation on it. And again, the annotation will have to contain the native layout of the struct, containing every information that the native compiler knows about it. For example, what is the padding? In this case, there are just two fields, 64-bit each. And the field have to be aligned with the name of the members in the interface. Once I have a struct interface, I can allocate it using a scope, using the allocate struct method and passing the class literal. So it's very easy. And when I have that, I can also call the accessor methods and basically treat it as if it were like a Java class. This is also very optimized because under the hood is using the unsafe API. The unsafe API is very well treated by the just-in-time compiler because there are a bunch of VM intrinsic in order to provide access to memory. So this will actually work really fast, even though it looks like Java code. And of course, sometimes C code wants to be able to pass functions as data. For example, a poster child of this is the qsort function. We need to be able to pass a callback that tells the qsort algorithm how to compare the elements. So we need to model something like this in Panama. And again, we are using interfaces with annotation. In this case, we have a functional interface called comp. We put an annotation called native callback in it and describe the signature, the native signature of the callback using our little DSL. Then we can allocate a callback using a scope. And when we allocate a callback, we can provide a lambda expression. The lambda expression will be essentially the code that needs to be executed whenever the callback is called by the qsort function. So in this case, I'm just returning the difference between the two elements. And then once we have a callback, we can just pass it out to our qsort function, and my Java code will be invoked. Of course, in order to make this work, the VM under the hood has to spin some piece of native code so that I have an entry point that I can pass to the native function to make it all work. So how is Panama doing so far? Well, we certainly, I think I hope I showed you that annotated interfaces are expressive enough to model quite a lot of stuff without using native methods. The workflow is definitely simpler, but there's still something that is not truly convincing me. Like, we've seen all these interfaces, like here. There's a lot of platform-dependent details that goes into writing those annotations. And if you imagine trying to port an entire library using this, for example, TensorFlow has 161 functions. So you have to write 161 annotations like this with platform-dependent details. It's very hard to get it wrong, and if you get it wrong, the binder will crash. It's not the story that we want to sell to users. So how do we make this better? Well, to make this better, we can just auto-generate all this stuff. So we introduce a tool called JExtract, which you can just point at the header file of the library that you want to use, and it will just generate all this stuff for you. So there is no need to manually write the interface and the annotation that I showed you in the previous slide. Of course, you can do it if you just want to call a single function. You can. But if you want just to import entire libraries, that doesn't scale. So it's better to use a tool that will do all that for you, and it will make no mistake. JExtract is based on the Clang parser API, so it will take advantage of all the information that the Clang parser knows about the library, and so it will be able to generate the exact layout for all the items that it encounters, with no ambiguity whatsoever. It also infers the right Java carrier type that is associated with all the function that it generates, and it has, while this is still a prototype, so it has many rough edges, it has been tested with real-world libraries: TensorFlow, OpenCL, OpenGL, Clang, Python, and the likes. And I'm going to show you a demo about OpenGL later. So this was the workflow that we left Panama with. We had a Java class, we compiled it, we get a class, and that was it. It was still better than JNI, but still we have to write the Java class, and it has annotations that are hard to write. With JExtract, the workflow becomes like this. So no longer you have to write the Java class. You just point JExtract at the header, in this case, the unistd.h, and JExtract will just generate a bundle of classes for you. As you can see, there's a lot of classes that JExtract generates, not just the one for the header. There's also a lot of annotation for the types that the header defines. And if we look inside, if we pick inside the header class, unistd.class, we will find many native methods, among which are getPid. So if we were to rewrite this code using the JExtract advantage, well, this will just become something like this. So you just import whatever Ackery JExtract has generated, and then you just bind, and you use the library. So we have been able to do in 4 or 5 lines what we were only able to do with an entire screen of code with JNI. So before I'll talk about performances, I want to show you a demo about OpenGL. Let me see if I can switch screen. Okay. Let's make it bigger. Can you see the code in the back? Yep. So this is basically, I'm no OpenGL expert, so that's the disclaimer. I mostly stitched together pieces of code that I found on the internet in order to draw a teapot and apply some texture on it. And with Panama, it's really simple to do that because it's very easy to go from the C code to the Panama equivalent of the same C code. So we need to use with OpenGL always these two libraries, GL and GLUT. And as you can see, my teapot is setting up a lot of off-heap arrays for the Lightning model here. And then it's even allocating a texture. And the way in OpenGL you allocate a texture is always by using some sort of library that allows you to open the image and extract the array of bits. Well, but we are in Java, and we have Swing. So why don't we just use the Swing API for reading the image, which supports quite a lot of formats? So here I'm giving an example of using the Swing API in order to load the image, to extract the array of bytes, allocate the array of bytes of heap, and then pass it to the OpenGL machinery in order to set up the texture. Then the example goes on. There are a bunch of functions that are all wired up into this main method, which is setting up the main window, setting up the size of the window, and then it's creating a teapot, and it's initializing a couple of callbacks. So here we see the callback mechanism in action. We are basically setting up a callback for the display function, which is here. And this display function is essentially clearing the screen, rotating the matrix a little bit, drawing a teapot, then popping the matrix and swap the buffers. Yeah, there is an inefficiency there, yeah. I just wanted to show that you can make the two API talk together. Of course, there are more optimal way to get this done. But I guess my point here is to prove that it kind of works. And let's see if it does. Yep. So I was able to cook this together in 20 minutes or so. So I didn't need to do anything too fancy. And just to give you an idea of the complexity of the libraries involved here, let's try to let IntelliJ decompile this class, this GL class. Let's look what's inside. It will take actually quite a bit. OK. And let's try to scroll down at the bottom. Oh, that's quite a lot of stuff. Yeah. It's 12,000 lines of decompiled code. So inside here, we can find anything like constants, functions, structs, callbacks, and it will be really a tall order to ask a Java developer to provide a full binding for this without having any tools. And that's why maintaining JNI bindings is so hard right now. There are, of course, bindings for OpenGL. And every time libraries are updated, then people have to write all this stuff all over again. So tools like JExtract completely eliminate that part of the process. So let's go back to the slide. Okay. So about performances, our main goal at this point was to achieve performance parity with JNI. We thought that, well, if you get a much simpler workflow using JExtract and the Panama API, and the performances are kind of on par with JNI, it's still a pretty good deal. So it should be enough to get people interested in trying to use this stuff. Of course, our longer-term goal is to improve over what JNI has to offer performance-wise, and I think I will show you one slide of how that's possible. So this is like the throughput of a get-build call. The higher the bar, the better. And you can see that already Panama is slightly faster than JNI. It's not anything to write home about. So I wouldn't choose Panama if you were after performance for this, because it's not going to change your life. But Vlad and I have been hacking on an alternate backend for Panama that is called Link to Native. This backend takes advantage of the fact that a lot of the complexities that surround native invocation are no longer needed if you're using Panama. So the kind of performance you can get with this alternate backend is like this. So getPid has a throughput that is 4 to 5 times faster, well, bigger, sorry, than the one that you get with JNI. And that's kind of the degree of performance improvement that Panama can bring. Of course, this is all experimental, it's crashing and burning, but we'll get it working at some point. This is an example for app calls. So I have qsort, it's calling my Java method, sorry, Java Lambda expression. And as you can see here, again, Panama is a little bit faster than JNI, which is good, but again, is nothing too exciting. What I wanted to point out here, we don't have any trick up on our sleeves for app calls yet, but I wanted to show you what is the difference between a qsort that uses an app call and a qsort invocation that doesn't use any app call, that does the callback mechanism in JNI entirely, so it remains in the native code. And as you can see, there's a 10x performance difference between remaining in native and doing an app call into Java. So that's the room of improvement that we have for Panama. And as we speak, I'm working with the C2 team in Hotspot. We are trying to get closer to that big vertical bar. And I think if we can do that, it's very important that we do that, because if we reduce the difference between writing programs in Java and accessing native libraries, people will start using these idioms more. They will start going back and forward between native and Java code more. So it's very crucial that we are able to improve the results in this particular case. So what we have seen, I think, it's a very good example of how Panama can improve your workflow when working with native code. There is also a rich API for handling off-heap data, which is, I think, a first time in Java. We can finally no longer use unsafe for doing low-level off-heap memory access. We have a blessed API that does just that. And it's also a safer alternative to JNI, because we have seen how scope uses ownership in order to control when a pointer can be the reference. So this API helps you getting your pointers in check. The room for performance, as we have seen, is huge for performance improvement, both with experiment that we have already tried and just by gauging at the difference between the native case and the JNI case. And it's not just for C. All the stuff that we've seen so far, it's very general. The DSL that I described for describing native memory layout is not language dependent, so you can use it, even repurpose it for describing network packets, message protocol schemas, and Panama is really a way to allow you to reach out to this off-heap data if you want it, even if you are not interested in using C or C++ libraries. So where we are now, I'm very pleased to announce that as of 2 days ago, I think, we managed to do it, we released binary snapshot so that you can just download and try them out. And unfortunately, we only support Mac OS and Linux x64 for now, so the platform support is limited. More will come. And we support, I think, most of the C feature except for the very exotic one, like if you want, for example, to model a function like macro, there's no support for it in Panama, so you will have to roll it your own. And the backend that we are using in this binary snapshot is the conservative JNI backend that gives you a little bit better performance than JNI, but not that much. So we are still working on getting the other more performant backend up in shape. Next, well, there's a lot of stuff that we still have to work on. First of all, it's not mentioned on this slide, but we need to work a lot on usability of JExtract. JExtract tool is cool, but there are still a lot of things that don't work correctly because it has to infer like what is the platform you're running on and try to import the right set of default libraries. And that's kind of hard to get right. Other than that, the next step will be to support complex API points, so things that typically are only known to the compiler, such as C++ templates, function like macro. So that's the next milestone there. And we want also to start looking into Panama as a serious value proposition for message protocol schema, which means supporting variable size layouts. So layouts whose size can depend on the value, on the length value, for example, that is stored in some field of the struct. We want also to apply the Panama medicine to the JDK itself. So we want to do a little bit of that and see if we can get rid of some of the native code in the JDK. We want to support Windows, and we have a lot of community effort in trying to get that up and running. So thanks to all the guys involved here. And of course, the optimization work is where all the action is with this project. So we plan to have a lot of discussion with the C2 guys, with the Graal guys, to figure out a way in which it's best to support some of these features. You can track the progress of this project in the Panama branch. And please, you're welcome to join the Panama-Dev mailing list and report your feedback and experience and comments and criticism, whatever you have to bring on the table is very welcome. And I think that's it for my talk. Thank you very much for listening. I think we have at least 5 minutes for the questions, if my clock is correct. Yep.
When should we anticipate this being part of the mainstream supported in our release? And second question, would you recommend rewriting existing JNI code to use it?
So the first question was when it will be part of JDK. You know that with the new release model, we can just target it whenever it's available. I think in reality what you will see is that part of Panama will be integrated sooner than others. So for example, the OFIP API has more chance, more likelihood to be integrated sooner because we already have discussed internally that this stuff can help byte buffer to overcome some of the limitations that are already there. So you may see this API coming to the JDK sooner than the rest of JExtract and all the other toolchain. But yes, it will be there when it's ready. And right now, as you have seen, not all the platforms are supported, so we still have a long way to go. Your second question was about should we rewrite our JNI code to use this? I think it depends. I mean, if you have JNI code you're confident with, you never have to replace it, because your libraries are stable and you're happy with the performances, then I think you're fine. It's up to you whether you want to use Panama or not. I think if you are in the business of providing bindings for some native library, for example, there are the TensorFlow Java binding, which are very unstable. There are the JCUDA binding for CUDA. If you are in that business, then it may be really worth to take a look at this stuff because it will basically slash 90% of the work that you have to do to keep those binding working. So it depends a lot on what is the use case.
It is ready to be used with BLAS libraries like OpenBLAS and Intel MKL, and they got right, should we expect some performance increase?
So BLAS, we plan to do an experiment soon on BLAS. I don't expect any problem, to be honest. We managed to get more complex libraries working, so I'm positive about that.
So it's still not ready to, you have to do experiments, right?
Yeah, but TensorFlow is working.
Okay.
So, and it's actually working faster than the Java binding for TensorFlow that is officially provided, because a lot of the code that in the TensorFlow official binding is written in native now can be moved into Java, and the just-in-time compiler can see that, And so we have benchmarks that are like 25% faster. Yes?
So one of the problems we have with JNI is we have C library to create giant arrays of double. And we end up having to copy those into Java. So will this help that problem?
Yes, because you can access your native array directly from Java without converting to a Java init array. Yes, definitely. The array class that I just briefly mentioned allows you exactly to do that. So you can point Panama to that location and create an array out of it.
Somehow that has to get free. So should we be responsible for knowing what memory free that was allocated in the C library?
Yeah, right now the free mechanism is handled by scope. So we are in the process of discussing what an API for allowing user define free strategies, how they will work in this setting. But yes, we'll get there. Yes? Yes, I think that you touch a very important point there. I think in reality, what I show you, yes, the extract is very cool, but what we want to give to Java developers is something that basically allows us to do the same thing that Jigsaw did for Java modules and do that for native libraries, so that you can just point your IDE to a native library, and then eventually you can just start using it. You don't have to just extract anything. And that means you need to be able to deploy artifacts that are self-described. So they contain the right library and some library loading mechanism that can pick up that library and load it depending on the platform you're on. So yes, we are considering adding support for what we are internally calling like multi-platform jar, or something that a distribution mechanism that will allow people to distribute some of this stuff, essentially, as Maven artifacts or Gradle or whatever. Yeah, I think it will be a critical part of getting this stuff more usable for regular Java developers that just want to use some API. They don't care about extracting things. Yep.
Is there anything here that allows you to call Java code from somewhere else in Python?
No. Panama is about Java calling something else. Yes, not the other way around. Yeah. Okay. Thank you very much for listening. I know it's the last day.